Neither one was complete, and it was even worse because like I can't remember seriously, I would love it. So we're going okay.
They're going to say,
You put an hour time. And then I opened it. 6.5 hours of your 1 hour. He really didn't think of it. You see the
oh, you're the toilet guy, right? Well, like, I buy something.
Okay, guys, let's start the class. Good afternoon, everybody.
Good afternoon.
How are you doing today? Bad?
It's too cold.
Yeah. I know it's the flu season. Also, some students are absent. Take care of your health. I know, so because my son was sick last night. I couldn't sleep, and he had a sore throat, cough, sneezing, headache. He's 3 years old. I know. Take care of yourself, especially when you are living on a kind of dormitory. So those areas are the infection are high. Okay. Let's start today's class. I try to just make it kind of loud voice based on the comments, but please accept me. I have some little cough, but I try to just bring my voice loud. We want to just today I'm going to talk about curvilinear motion in different coordinate system and the graph of the curvilinear motion, and we will go to the dependent motion analysis. For a curvilinear motion in this new coordinate system, what you're going to learn today, first, you understand the meaning of radial and transverse motion. And second, you determine the velocity and acceleration components in symmetrical coordinate. And finally, you apply the equations to particle motion analysis through examples. I will show you some applications, how to find the velocity component and acceleration components. And now, before I show you some of the applications, can you explain or just tell me where do you see circular or radial motion or in real life. For example, think about vehicles, rotating arms, satellites. Those are some examples. Where do you see circular or radial motion in real life? Yes?
Wind turbines?
Wind turbines. Other students? Yes?
Clock.
Clock. Yes?
Ferris wheels.
Sorry.
Ferris wheels.
Yeah. Other. I got 3 answers. Yes? Distance. Yes. Other.
Like wheels on like a car.
Correct. Wheels on the car. Other. Yes.
Turbines that I cited too.
Turbine. Just mentioned. Yeah. Correct. Other. Other applications. Is there some of you working on robots or robotic teams? Robots. Are those applications for curvilinear motion and use a kind of radial and transfer motion? Okay. These are some applications, mostly interested in the 2D. This is the arm of robots. The robot arm will change in the direction of the R. I will explain about this coordinate system next slide. And you will see this application or this type of mechanisms. For example, this type of mechanism is there is a link, and this link rotates and cause this head point moves along this slot. This type of mechanism, for example, in small scale, for example, if you saw some of videos in the internet, you assemble some of the watch, for example, Swiss watches. Some of those very small kind of mechanisms are used on those rotatory, for example, ones. Or robots. These are one examples, and other examples you mentioned about turbine blades, turbine pistons, wheels. We can use this coordinate system. And what is this coordinate? And how we can draw the axis in radial and transverse direction. Consider a particle moves along a curved path, and we can find the position of the particle in this space, in this 2D space. If this is the plane, and we want to find the position of the particle anytime in this space, we need to use r and theta. This r is the radial distance from the origin, and theta is the angular position. If I just put this particle any point in this slide or this plane, you need to have the r and theta to show me the position of the particle. Now, how we can draw the r-axis and theta axis for a curvilinear motion? To draw r-axis, you can see that this one is a particle. The blue line is a curved path. And this r shows the position. It's a vector. We can draw a vector from origin to the particle position. R shows the vector, and theta is the angular position. Now, if I extend the r vector outward, this will be the r-axis, or is called radial axis. Radial axis is along the r vector, and it is outward, not inward, outward. And also theta axis, if I draw a vertical line or perpendicular line to the r-axis, this line, that is perpendicular to the r, and the correct or positive direction of the theta will be in the counterclockwise direction. If this one as a clock. Clocks rotates in this direction called CW or clockwise. The opposite direction is counterclockwise. If this particle is moving this direction during the time, for example, at T1 is in here, at T2 is in here, T3 is in here, this particle is moving in this direction. And this is exactly in the direction of counterclockwise direction. And theta is positive in counterclockwise direction. Also, if you remember, for the x-axis, we use I as a unit vector. And also for the y-axis, we use j as the unit vector. And if you remember, for a tangential and normal axis, we use u sub t and u sub n. These are the unit vectors. We use the unit vectors to show the direction. In the radial and theta axis, or radial or theta, just I forgot to mention, theta is called transverse axis. Now, I will introduce the UR, U sub R, and U sub theta. These are the unit vectors along the radial direction or R-axis. U theta is a unit vector along transverse direction or theta axis. Now, I explained about the polar coordinate. This is called polar coordinate. It's a 2D problem. For a 3D one, it will become a cylindrical coordinate that I will explain later. But for a 2D problem, we use R and theta axis to show the motion of a particle when it has a curvilinear motion. Now, question: if a particle moves along a perfect circle, which coordinate stays constant? Yes.
Radial distance is equal distance point.
Exactly. For a perfect circle, R is constant, and R will be constant, and this coordinate is always constant. Now, move to the next slide. I want to explain how we can find the velocity. In this slide, you see that we used R vector and theta, or this coordinate, to show the position of the particle in a kind of polar coordinate system. Now, to find the velocity, if you remember, velocity vector, it is tangent to the path. If I want to draw the velocity vector, let me erase this. If I want to draw the velocity vector, it is tangent to the path. Okay? You know about this. Also, it was a part of a question you answered during the exam 1. What is the direction of velocity? It's tangent to the path. This velocity vector has two components, one along R, one along theta direction. You will see that we can find the component of velocity along R. This one we'll call V sub R, and this will be the velocity direction along theta. Now, to find the velocity for the kind of this, you remember that velocity It is the derivative of the r with respect to time. You know about this. This is a general equation. It values for any type of the motion. Now, if you have the r, what is the r? In this coordinate system, using this r vector will have the r as a magnitude, and the direction will be along the r direction. This is how we can find the position in this coordinate system. Now, to find the velocity, I need to put this r into this equation, take the derivative to find the velocity vectors, our velocity components. Can move to the next slide. Any questions? No? Okay. If we substitute this one into this equation and take the derivative, I skip the proof how we can find the components in detail, but I will show you the final product. To find the velocity component in polar coordinate system, the velocity of the particle will be given by this vector. As I explained in the previous slide, velocity has two components, along r, along theta. I can write the velocity vector in terms of the velocity vector along r, and this is the velocity vector along the theta. VR and V theta are the magnitudes. UR and U theta are the unit vectors that show the directions. Now, what is the VR? If you put in the derivatives and find this components, VR or radial velocity will be R dot, or the rate of the increase or decrease in the length of the radial coordinate system. For example, if this particle move here or other places, if this one is R1, this will be R2, this will be R3, and finally this will be R4. You will see that the R will be changed during the time. This is at, for example, T1, T2, T3, T4. R will be changed. Means that if R is changed during the time, it's related to the radial velocity or this component. And velocity along the theta or transfer velocity can be defined using r theta dot. This rate of the velocity will be along the circumference of a circle having a radius of the r. Now, if you remember in the previous lecture, I talked about the r theta dot. Do you remember what is theta dot is called? Does anybody know this theta dot? What does it mean? Or what is called? Theta dot is the derivative of theta with respect to time. What is theta dot called? Yes?
The angular velocity.
Correct. It's an angular velocity. This theta dot is called angular velocity. This theta dot is an angular velocity. The unit will be radian per second. This type of velocity will be used for rotating bodies. For example, for a fan, it's rotating with the angular velocity. If this theta dot is high, just as you can see, the kind of fan moves fast. But if it's slow, this theta dot has a low number. And these are the velocity components. It means that here, is the r dot, v theta is the r theta dot. This is called radial velocity. And this one is the transverse one. Usually, most of the time, I will ask you to find their magnitudes. I do not ask you to write the vectors in the velocity in the vector forms. I will ask you to find the magnitude of the velocity. These are the magnitude of velocity along the r and the magnitude of velocity along the theta directions. Now, can I move next slide? Okay. One question. I want to ask you this called thing for sure. If r dot is 0 and theta dot is not 0, can you guess, or what do you think, which velocity component does exist? Vr or v theta? First of all, I want to all of you think by yourself, pair with your friend, your neighbor, then share with me or share with class. Let me write the equations also for you. Vr is the r dot. V theta is the r theta dot. Which one exists? Did you reach to the answer? Can somebody share? Which one? Which component does exist? Yes. If you can see here, r dot is 0, and this radial velocity will be 0. But because this one is not 0, this term does exist. This term does not exist. The example of this one, I try to draw a perfect circle, but please accept. If this is a circle, I know it's not a circle. If this one is a circle, circle means that the radius is constant. If there's a car, it's moving along a circular path. For this type of example, because r is constant, okay? R is constant, means that r dot will be 0. And also, if I ask you to draw the velocity components at this position, for example, here, this will be the r direction, and this will be the theta direction, for example, at this position. This will be the velocity along the r, and this will be the velocity along the theta direction. At this position, also you can see that this term or this component does not exist because the velocity, it is tangent to the path, it is tangent to the v theta. This is the reason v theta is exist, vr does not exist. Or move to another position. Here, if the car moves here, okay? I ask you to draw the r and theta vectors. Just I erase this. At this position, this will be the r-axis. This will be the theta axis. The velocity vector at this position will be in this direction. Means that it is aligned with the theta axis. This is the reason we have VR and we do not have VR, but V theta does exist. Any questions? Now you can understand how we can draw our theta axis, what are the velocity components, and how we can relate this velocity with the r dot and theta dot. Bless you. Can I move to the next slide? Yes. Yes. Now I want to find the acceleration in cylindrical coordinate system. From previous equation, we found the velocity vector, that it was VR UR plus V theta U theta, that VR is R dot UR plus R theta dot U theta. To find the acceleration, acceleration can be found from this equation, derivative of velocity with respect to time. If you substitute this velocity into this equation and take the derivative, you can find the acceleration vector or the components of the acceleration along the r and theta directions. The proof of this one will be on next slide. I skip. I will show you the final product. But if you are interested, next slide shows that how to find the acceleration components. What are the acceleration components? You will see if it's a particle, this is an acceleration vector. Acceleration has one component along the r, one component along the theta, and these are the equations that we can find the magnitude of the acceleration along the r and the magnitude of the acceleration along the theta directions. You will see there are several terms or expression in here. For example, r double dot can be found by second derivative of the r with respect to time squared, or the derivative of the r dot with respect to time. And theta double dot is the second derivative of theta with respect to time squared, or the derivative of theta dot with respect to time. Now, r double dot is the change of the r dots. If you remember, r dot, it was the velocity along the r with respect to time. It means that the change of the velocity along the r with respect to time, you can find the r double dots. My question from you, what is theta double dot is called? Yes, angular acceleration, correct. Theta double dot is called angular acceleration. The unit of this one is a radian per second squared. Also, these terms minus r theta dot squared is called centripetal acceleration or inward acceleration. 2r dot theta dot is called Coriolis type effect, or this type of the acceleration for the rotating bodies. These two terms, you will see, I explained about the r double dot, I explained about the theta double dot. This term shows the change of the theta with respect to time, change of the theta dot with respect to time. And this one is the inward acceleration. This one has a Coriolis type effect. From this one, okay, if you are rotating on a circular path, if you're driving on a circular path, for example, just it's a car, it's your car, just you want to just move along a circular path. Okay? If this one is the r direction at this position, and this one is the theta direction, this term of acceleration causes that you feel some forces toward the center of the kind of this curve. If you try, when you want to change your direction, if you just change the direction from I-75 to the I-69 or those kind of other highways, you will feel this one. And this is related with the rotation of the body. Okay, any questions? Can I move to the next slide? Yes. This slide, I just put it here. This is how we can find the acceleration components. This is for you. Just if you are interested to find the component of the acceleration, this is, I explain how to find the components. This is for your information. You do not need to just find those acceleration values for the exam. I will provide all equations as you saw for the exam 1. Now, how about a particle? It has a motion in a 3D space, and we want to use a coordinate system that can describe the motion of the particle in the 3D space. To use and also describe the motion of the particle, we will use a cylindrical coordinate system. As you can see, I added one more coordinate, z direction, to show the direction or the motion of the particle in 3D space. This is the only axis I added. For the 2D, just we use the polar coordinate. I add the z. This is the z-axis. To show that how this particle moves along the z-axis or change the height of this one in the 3D space. For example, this one, the blue one, shows the motion in the 2D, but if the particle change from this plane goes to the 3D space, we added this direction, or z direction, or uz, shows the unit vector along the z direction. To show the position, if you remember, I explained about this one and show you the velocity components in the polar coordinate system. And these equations that they are in the box, these are shows the position, velocity, and acceleration in a 2D motion. But for describing the motion in the 3D space, I added these expressions. For all of them, I add z to show the position in the z direction, then take the derivative of this one with respect to time, It will be z dot to show the velocity along the z direction. And finally, this term shows the acceleration along the z direction. Compared to the previous equations, these terms are extra expressions. This one, z dot, shows the velocity along the z. Z double dot shows the acceleration along the z direction. What is the application of this one? One application is the robot arm. In a 3D space, if you want to just find the position of the hand in a tree, and you have 3 coordinates, r, theta, and z, you can use this one to show the position, then take the derivative to find the velocity, and also take the derivative of this one to find the acceleration. Why is needed? For example, this is for example, a robot arm. Okay. Now, as an engineer, you want to design this one and control the motion of the robot arm. For example, this robot arm wants to catch or hold a kind of very sensitive part. The velocity and also the forces that apply to this sensitive part or very just thin part is important. How do you find the forces along the arm, theta, and z? You have the acceleration. If this is the robot arm, and this will be the r-axis, this will be the theta axis, and also in this direction will be z. If you want to design this one in a 2D, this is small. But for a 3D, you add this z, just move along the z direction. Now, you have the acceleration along r and theta, for example. You can find the forces along the r and theta. Or you have the velocity along the r and theta. Then, based on this one, you can design the kind of angular acceleration or select a motor to rotate this arm with certain angular velocity or certain angular acceleration. This is how you need this information. And dynamic help you to select a motor and just design this robot arm. Also, we have the control electronics. I know those ones. This is from this part to find the velocity arm and also the acceleration of the arm. Any questions? Okay. Can I move to the next slide? The solution structure, I just made my, based on what comments you just gave me, I appreciate all of your comments. I have to also read remaining comments. Some of comments just mentioned, just some of slides are wordy. I just tried to decrease some of the words from slides, make it very simple. The solution structure for a problem to identify first to find r, r dot, and r double dot, also identify theta, theta dot, and theta double dot, then substitute those values into these 2 equations for the velocity and substitute into these 2 equations to find the acceleration components. This is the solution structure. Any problem you have and you want to describe the curvilinear motion using polar or cylindrical coordinate, this is the solution structure. Can I move to the next slide? Just wait. I will show you the structure with the examples I want to solve in the next slides. Can I move to the next slide? Okay. Can I move to the next slide? This slide I captured from the book. For some of you, you do not have access to the references. I just put this slides. It summarizes what I explained for the first part of the lecture. And also, I just summarized the equations. You do not need to just go through all the slides to find the equations. Also, if you forgot to just write it, this slide help you to find the formula and also review this part of the lecture. This is for your reference. Now, scan this barcode. Answer these two questions. It's a class participation. Please, all students, participate in class participation. First question, you want to find what is the R dot term, and the second one, if theta changes the time, what type of velocity component does this contribute to? Did you answer the questions? Who needs more time? Okay. I'm taking my vitamin C. Can I show the results? Yes? Let me see how you answer the questions. Okay. First question, 83% answered correctly. Second question, 69%. Now, thank you. First question, what does the term R dot represent in the cylindrical coordinate? The term R dot is the rate of the change in radial distance. R dot is the derivative of the R with respect to time. In mathematics, this means that the rate of the change in radial distance. This is not the angular velocity because the angular velocity is v theta. Okay? This is not changing angle or theta dots. Also, this one is not acceleration. Acceleration, it wants to be an acceleration, it should be r double dots. For the second question, if theta changes with time, what type of velocity component does this contribute to? For the exam, I will not put the equations in the front of the questions. You have to find the equation from the equation sheet as you did it for the exam 1. But for this one, there's a theta also from the kind of the options. You will see some radial, VR, v theta. You can find those ones from the equation sheet. And if theta change with time, means that theta dots. What component of the velocity? This component is not. Why? Because it changed with the r dots. This is not correct. Also, this one also is not correct. Why? The Vz will be related to change with the z direction. Also, this one is not correct. This is the correct answer. B. For the first one, C. Any questions? No. Move to the examples. There's a slotted link P at the O at the result of constant angular velocity. This drives peg moves along this kind of spiral guide, and we want to find the radial and transverse component of velocity and acceleration at instant of theta equal to pi over 3. This is one example. Now I will give you 1 or 2 minutes. Just write whatever you want to write or think about how we can solve this problem. Then I will start to solve it. Okay, for this type of problem, what is given theta dot is given, and also it is constant. Theta dot, it is 3 radian per second. The spiral guide, this is the guide. The equation is given 0.4 theta. Also, at theta of pi over 3 radian, what we are looking for to find, we are looking for to find the radial and transverse component of velocity and acceleration. We are looking for VR. We are looking for v theta. Also, we are looking for AR and A theta. To solve this problem, solution. I will use the polar coordinate system for a curvilinear motion. Look, this particle, this peg, is moving along this curved path. You know it's a curvilinear motion. Also, whatever is given to you, you saw in the problem, the components or the variables given in this problem is based on r and theta. You will need to select the polar coordinate and show the motion of this P or peg P in polar coordinate system. What's the coordinate at this point? Look, this is the r vector. R-axis along the r, outward. Theta axis will be perpendicular in the counterclockwise direction. And here, at this point, if this is the velocity, we want to find the component of velocity along r. This is the VR. The component of velocity along the theta or v theta. Also, we are looking to find the acceleration. For example, this is an acceleration. We are looking to find a r and also a theta. First, if I divide this problem, I want to first find the velocity components, then I will find the acceleration components. To find them, they're based on the equations that we have. For example, velocity along the r, it can be found from r dot. Velocity along the theta can be found from r theta dots. To find the velocity along the r, I need to find the derivative of the r with respect to time. We have r, we have the theta dots. To find the r dots, next slide. Can I move to the next slide? Okay. R, it is 0.4, if I'm correct, theta. R dot is the derivative of the r with respect to time, or the derivative of 0.4 theta with respect to time. The derivative of this one is easy. It's 0.4 derivative of theta with respect to time. That this term is theta dots. Also, r double dot is the derivative of it's a second derivative of the r with respect to time squared, or it is the derivative of the r dot with respect to time. These are all same. Or the derivative of the r dot will be the derivative of the 0.4 theta dot with respect to time, that this derivative will be 0.4 theta double dots. Now we have all of these values. How? To find the r will be 0.4. Theta is given to you, pi over 3. If we calculate this one, 0.4 multiplied by pi divided by 3, it is 0.2. I just round this. 0.42 meter. At this position, at the instant of theta, pi over 3, r is 0.42. R dot also, theta dot is given in the problem, 0.4. Theta dot, it is 3. R dot is 1.2 meter per second. Also, we can find the R double dots. We have theta dots 3 radian per second. Can somebody tell me how much is theta double dots? How much is theta double dots? If theta dot is 3, how much is theta double dot? Yes?
0.
0. Why? Constant. That was easy. Theta double dot is the derivative of theta dot with respect to time. The derivative of 3 with respect to time is 0. Now, R double dot will be 0.4 multiplied by 0. It's 0. Meter per second. Now, first one, we want to find the component of velocity. Velocity along the R, it is R dot. Velocity along the theta, it is R theta dot. We have the R dot, 1.2 meter per second. Also, velocity along the R, 0.42 multiplied by theta dot. Theta dot also is 3. If we calculate this one, 0.42 multiplied by 3 is 1.26 meter per second. These are two simple ones. First part, I found the velocity components. The next part, I want to find the acceleration. Oh, it's not easy to draw. Next part, I want to find the acceleration components. To find the acceleration components, these are the equations we need to find. Acceleration on the R, it is R double dots I cannot remember, minus R theta the square and A theta, it is R theta double dots plus 2 R dots theta dots. Also, these are easy too. We have all of the components. We have R double dot, we have R theta dots, theta double dot. We have to substitute the values into this equation. That was the easy part. Now, R double dot is 0. R, it is 0.42. Theta dot, it is 3 squared. We try to calculate this one. It is 9 multiplied by 0.42 is 3.78, or 3.78 minus, this is the meter per second square. Also, to find the R acceleration on the theta, we have the R, it is 0.42, theta double dot, it is 0, plus 2, R dot is 1.2, theta dot, it is 3. Sorry. Now we can find this one. This will be 7.2 meter per second square. or let me write this one here. This will be minus 3.78 meter per second. Also, these are one answer and one answer. Got it? First example. Any questions? I can start to solve second one, or do you want to go to break? Which one? The second one is a little bit long. Maybe take 10 to 15 minutes. What do you like? Second one, I start to solve, or do you want to go break? Break. Go break. Now it's 221, come back 226. Let's resume the second part of the class. Any question from first part? No? So far so good? Okay, let's go to the next example. This is a example regarding the bucket of backhoe or excavator. The path of the cardio is given as a function of theta. We want to find the magnitude of velocity and acceleration of the bucket when theta is 120 degrees. And when the boom is rotating, the angular velocity of theta dot 2 radian per second, and angular acceleration of the theta double dot 0.2 radian per second squared. This is one example regarding real-world applications. Now, for this, the position of this anytime is given using R. What is given? R is 25, 1 multiply 1 minus cosine theta. At theta 120 degree, R, it is at this specific or instant angle. It is 25 multiply 1 minus cosine of 120 degree. If we calculate this one, one minus 120, and then cosine, and multiply by 25. It is 25 multiplied by 1 minus cosine of 120 degree. It is 37.5 foot. And also, theta is given 120 degree. Theta dot, it is 2 radian per second. And also, theta double dot, it is 0.2 radian per second square. At this instance, we are looking for to find the magnitude of velocity that can be found from this equation, VR squared plus V theta squared, and also the magnitude of the acceleration can be found by using the summation of the AR squared plus A theta squared, and then goes to the square root. We need to find magnitude of velocity and magnitude of the acceleration. To find their magnitudes, we need to find their components, VR, V theta, AR, and A theta. Now, if I divide this problem into two parts, when first, I want to solve the velocity component, or the magnitude of velocity first. To find the magnitude of velocity, we need to find the VR and V theta. VR is the R dot, V theta is the R theta dot. We can find the V theta. Why? We have the R, 37.5, multiplied by theta dot 2. We can easily find the velocity component along the theta, that if I multiply this one by 2, it is 75. 75 feet per second. Easiest part. Also, to find the velocity component along the r, I need to find the derivative of the r with respect to time. Or I need to find the derivative of 25 multiply 1 minus cosine theta with respect to time. Now, can somebody calculate this derivative for me? What is the derivative of 25 multiply 1 minus cosine theta with respect to time? How much? Sine of 120. I just collect your answers. Sine of 120. Or do not substitute your values. You can give me the expression. 25. Okay, 25. Other students. One of the comments from you, one of you mentioned that I do not like the tricky questions. This is the tricky one. Sorry, this is a part of the questions. This is not tricky. This is related to your knowledge in mathematics, not related to my course. How much is the derivative of this expression with respect to time? How much? Or can you give me the expression? Try it. It's a common mistake I have seen from my previous students. Unfortunately, I do not know what's the root or what's the problem. Most of the students, they struggle to find this derivative. This is the reason I stopped and asked you this question. Yes? You changed your answer?
Yeah.
What?
I, for some reason, thought it was not 25 sine root theta times theta.
Derivative multiplied by theta by theta?
Dot. Instead of 25.
Multiplied by theta dot? Or
No 120. So 120 is replaced with theta dot
okay.
Times theta.
120 is replaced with theta dot?
Yeah. Times theta.
Times theta. Okay.
Outside.
Theta is outside.
Or normal theta is on outside.
Okay. Normal theta is an outside. How? Yes.
0.
0? I collect your answers. It's good. Just challenge. Try. Unfortunately, students challenge themselves in the exam. And in the exam, it's not their place to see and also solve these derivatives. How much? Other students on the corner, back of the class, this side, middle. Any idea? It's a common mistake. Just I want all of you solve. Hey, look, the derivative of 25 multiply 1 minus cosine theta with respect to time. What I do, okay, first, I multiply this by this. It's 25 minus 25 cosine theta with respect to time. The derivative of first term with respect to time is 0. It's a constant. But the derivative of minus derivative of 25 cosine theta with respect to time, it will be, this one will be minus 25 derivative of cosine theta with respect to time. This one, theta is not is a function of the time. Or to find this, we can relate this one using chain rule. What? I can write this one as a derivative of cosine theta with respect to time, with respect to theta, multiplied by derivative of theta with respect to time. This is called chain rule. Or if you are not looking for the, or do not remember this one, add in theta with denominator and denominator. This is exactly the same as this. Now, this term, it will be minus sine theta. This term is theta dots. Means that this will be minus 25 multiplied by minus sine theta multiplied by theta dot. It is 25 sine theta, theta dots. Okay, now we found the R dots in here. Now substitute 25 sine 120 multiplied by theta dot is 2. We want to find it. It's a sine 120 multiplied by 50. It is equal to 43.3 foot per second. Okay? Now, we found the R dots. Return back to the previous one. This is R dots. Means that velocity along the R, it is 43.3 foot per second. Any questions? Okay. Now, we have the VR and also we have the V theta. The magnitude of the velocity will be the square root of the 43.3 square plus 75 square. If we calculate this one, it is 75 square plus 43.3 square equal to, and then square root of this one, 86, 75 square plus 43.3
3 square equal to this. Now the square root of this, it is 83.6. 80, how much? 86.6 foot per second. This is first part. For the second part, we want to find the acceleration. To find the acceleration, we want to find this component, AR and AT. AR, it is R double dot minus R theta dot squares, and A theta, it is R double dot R theta double dot plus 2R dots theta dots. Let's start with this one. This is an easiest one. We have the R from previous one. We have 37.5 multiplied by 0.2 plus 2R dot. We have this one, 43.3 multiplied by 2. If you calculate this one, $37.5 multiplied by 0.2 plus 4 multiplied by 43.3, and then this equal, this will be 180.2 per second squared. Now, we want to find the R double dots for this one. Okay? To find the R double dot, we have the R dot from previous one. Look, the R dot, what I found here is 25 sine theta, theta dots. Means that the R double dots, it is the derivative of the R dot with respect to time, or it is the derivative of the 25 sine theta, theta dot with respect to time. Okay. Now, to solve this one, look, I will use the product rule. There is several solutions. Look, guys, you do not have to just use my solution only. Maybe you learn other solution from your calculus 1, calculus 2. Just follow those ones. You do not have to just follow same solution I just solved for this problem. But, for example, for this one, it is 25 derivative of sine theta, theta dot with respect to time. I will use the product rule first, means that the derivative of sine theta with respect to time multiplied by theta dot plus the derivative of second term with respect to time multiplied by sine theta. Okay. This one will be theta dot cosine theta. This term will be theta double dots. To find this, I use the chain rule. I do not write the details now, just I skip it. Now, substitute the values we have. 25 theta dot is 2 multiplied by cosine of 120 degree multiplied by 2 again plus theta double dot, it is 0.2 multiplied by sine of 120 degree. Now, we calculate. it is 4 multiplied by the first parenthesis 120-degree cosine, then plus the 0.2 multiplied by 120 sine, close the parenthesis, equal, and then whole brackets multiplied by 25. This will be minus 45.7. This will be minus 45.7 means the foot per second squared. Now, put into this equations, minus 45.7 minus 37.5 multiplied by 2 square. This will be the acceleration along the R. Now, plus 45.7. This is 195. 195.7 foot per second squared. Now, the magnitude of the acceleration can be found using AR squared plus A theta squared, or 195.7 squared plus 180.2 squared. If you calculate this one, (195.7) squared plus 180.2 squared equal to, and the square root of this one is 266.03. 266.03 foot per second squared. This is the answer I'm looking for. Now, what I want to mention that, look guys, if you cannot calculate the R dots for this problem, you cannot find the A theta correctly. Also, you cannot find the AR also correctly. Also, you cannot find the A correctly and also the B correctly. This simple mistake, it took at least 5 to 6 points out of 20. Got it? 5 to 6 points out of 20 for this simple mistake if you cannot find it. I know some of you, you know those ones, some of you, you do not know. But please practice. I will give you some problems for the exam, for the just practical examples. Just find those ones. For the second exam, you will have one problem. Got it? What? Single problem. No, similar problem. Okay? The reason that exactly just mentioned in my all classes, I know, I do not know what's the kind of issue, but most of the students, they have struggled to find this derivatives.
practice. By practice, you can get, and also you can learn it, or you can review it. Any questions? No questions? Okay. The next part of the lecture is about dependent motion. I will explain what is a type of dependent motion. Then I will explain how to relate position, velocity, and acceleration of the particles that they have a dependent motion. And we solve problems using a systematic procedure. Before I just move to the next slide, can you tell me where have you seen motion that they are linked or constrained? Tell me what type of motions you have seen that they are linked or constrained. One application. Yes.
Suspension.
What?
Suspension.
Suspension of the car. Okay. Other students. Yes.
I think maybe like wires or people.
Right. Yes. This is the another one. Other. Yes. Yes. That's a good one. I like it. Other examples. No? Let me first explain, then I will show you other applications. Dependent motion is a type of the motion that the motion of one particle depends to the motion of another one. These are some examples commonly used for dependent motion. Cables, pulleys, rigid connections. As your friend mentioned, some of those examples related to cables, pulleys, rigid connectors, suspension. The motion of one depends to the motion of another one. It means that you cannot choose the motions independently. Okay? Now, what are the applications? These are some of the applications. These pulley systems you will see everywhere. And for example, for this one, this car related the motion with the motion of the motor that rotates the cables. Also, this car, it moves to the right because this one moves upward. Or this pulley system is used to just move heavy loads using a pulley systems. Now, one question, for example, if I pull this cables or this rope downward, what do you expect for this block? Do you expect this block goes upward or downward? Upward. Okay? This is exactly when one motion moves up or down, another one just moves in another direction. For example, I bring this one downward, this one goes upward. This car moves to the right, this box or this heavy load goes upward. Or this one is rotating upward, causing this one, this cart moving up to the hill. Now, how we can write and relate their motions from this very basic example. Consider two particles
Why? This one is a particle A. This one is a particle B. Or this can be both. They can be a kind of rigid bodies. They are connected using a cable or a cord. This cord is an inextensible cord. What does it mean? It means that the length of the cord, it is constant. It doesn't change with time. Also, to write a position coordinate system, I will select a datum line here. Based on this datum line, SA shows the position of the block A or particle that going downward or upward. SA will be changed during the time. Or this particles, if I divide that, both, they have a rectilinear motion. Also for the particle B, I will select a kind of datum line, and SB shows the position of the B during the time. Also, SA and SD shows the length of the cord. When the change of this length or change of this length, the position will be changed for the A and B. To write the position coordinates, first I will write the total length of the cord. What is the total length of the cord? It's this length of the cord plus the cord along the pulley plus SB. This is the total length of the cord that they're just wrote in here. Now, from this position coordinate system or equation, I want to find the velocity and relate the velocity of the block A with velocity of the block B. Now, if I have this position equation, how can I relate them? How can I find the velocity if I have the position equation? If I have the position equation, how can I relate velocity of the A with the B? Or how can I find the velocity equation? How? Yes. Correct. By finding the derivative of this equation, I can find the velocities. If I take the derivative of this equation, look, the derivative of all of these expressions, this, and this one. Take the derivative. Derivative of SA with respect to time plus the derivative of LCD with respect to time plus the derivative of SP with respect to time equal to derivative of LT with respect to time. Now, question. What is this term called? The derivative of SA with respect to time. SA shows the position of the block A or particle A. What is the derivative of SA with respect to time is called? What? I hear somewhere. What is this derivative is called? Yes. Velocity. Yes. It is the velocity of the A or velocity of the block A. And also similar for this term. This term shows the velocity of the block B. Next question. How much is the derivative of LCD or this length of the cord that is along the pulley system? How much is the derivative of LCD with respect to time and why?
How much is it? It's 0. Because the length of the cord around the pulley is always constant. The length does not change. The contact with the pulley does not change. This term is 0. Now how about this term? What is the derivative of total length of the cord with respect to time? Does it change with time? Does it change with time, the total length of the cord? No. Why? I just mentioned this is an inextensible cord. It's constant. The cord does not deform. This is an assumption. This will be 0. This is also will be 0. Then we can conclude from this one that velocity of the A plus velocity of the B equal to 0, or velocity of the A equal minus velocity of the B, or vice versa. What does it mean? It means that if you have the velocity of one of particles, you can find the velocity of another particle. This is called dependent motion. If you do not have the velocity of block B, you cannot find the velocity of the A. Okay? These are dependent motion. Same for the acceleration. Also, if I take the derivative of this equation, I can find the acceleration relations. The acceleration of the B is equal to acceleration of the A, but it is in negative direction. Also for the velocity, if just bring this one downward, this one goes upward. Based on the datum line you select, this is the positive direction. This one going downward, this one goes upward, is negative. This is the reason you will see this negative signs in here. And it is consistent with the motion of this system. This example shows how we can relate and find the dependent motion equations. Okay? Okay, move to the next slide. Now, what is the procedure for dependent motion as I did it in the previous slide? First, I will define the position coordinates. What is the direction of SA, SB, and those ones. Then write the cable length equation. By taking the derivative of this length equation, I can find the velocity relation. And by taking the derivative of velocity, I can relate their acceleration. And finally, we apply sign convention carefully. Okay? Sometimes this is an important one for complex problems. This is the procedure. I will show you on the example we have at the end of today's lecture. Okay. For example, for previous one, I just defined this is SA, this is SV from this datum lines. Then write the cable length. LT is SA plus LCD plus SB, and then I take the derivative of LT with respect to time and found that velocity of the A equal minus velocity of the B. Then I take the derivative of velocity with respect to time, and I found that the acceleration of the A is equal to minus acceleration of the B, and also apply the sign convention. Just if going upward, one going downward, this equation shows those relations.
Now, I have one question for you. If you want to just go step by step and solve a dependent motion analysis, which step do you think that you will skip? Which step do you think that you will skip? Which one? The first one, the position coordinate system. Other students. Which step do you think that you will just cancel or just you will eliminate? Yes. Sign convention. Okay. Good one. I want to mention these are common mistakes. First, they forgetting the negative signs, the sign conventions. Also, writing velocity equation before position equation. Also, using inconsistent coordinate directions. These are the common mistakes I have seen from my previous students. Okay. Now, the next example is an interesting example. I already uploaded, but can I move to the next example? There's a summary and then there's an example. Oh no, this is an example. That example is related to your real life. You just go to the gym and you want to just lift those heavy ones. I never tried those ones. If this is an athlete, once he pulls the handle to the left with a velocity of the 0.5 meters per second, we want to find the velocity of block B. This is how you can relate dynamics with your real life. I just selected those ones. Previous courses, I just selected a very common pulley system, but this one shows you the pulley system or an elevator problem. Okay, to solve this problem, okay, first, you will see there's one cord or one cable. This one. Look. This going down around this pulley. Sorry, I just made not good one. This is a one cord, one cable. Just if you saw, and if you cannot track this one, it means that there is not one cord, there's two cords, two cables. For this one, we have one cord, one cable. Now, we have one position equation because we want to find the total length of one cord. First, if I select this one, A, I try to name them correctly. B, C, D, E, F, G, H, I, J. You do not need to repeat those ones. Just first example, I have to just go through the detail. For next one, I will omit and also eliminate those details. Why I divide this ones? I want to know which parts are related to the kind of around the pulleys and those other segments. And I want to write the length of all of cords. First step, I want to write the position equation or the total length of the cord. Now, first I need to just put the coordinate. For example, if I select the datum line for here, and in this direction is a positive direction, and this length, it is SA, based on how much are you strong, you can push this one, and this length will be changed. Do you agree? For some of you go to the gym, you know those ones. But my doctor recommended me go to the gym, but I didn't listen. But go to the gym. It's good for your health. Now, also, if this one is changed, this one goes up and down. Just moving this one to the left, this one causes this one up. This one, when this one goes up, this lengths will be changed. Okay? That's the easy one. The lengths that will be changed. Also, I will select this one as a datum line. Based on this datum line, there's lengths that also will be changed in this direction called SB. Now, first, I just established the coordinate system. Then, we have 10 minutes. Let me just move. I want to write the position equation. To write the position equation, I need to write the total length of the cord. The total length consists of the length of all of the segments I just write. I will write it Yeah, I finished. Okay? You do not need to repeat this once, okay? Just exactly, just I need to just detail for some of you, maybe you want to follow. But final, the reason that I write those ones here, all segments, I just write this total equation. Now we have some of them, for example, L of the length of the AB, we have SA, okay? Whatever I have, just I substitute. Look, we have SA. This one is SA. Also, this GH, this one, and this one, and this one also, with this one will be also SP. Means that the GH will be SP, the IJ will be SP, the MN also will be SP, and also the KL also will be SP. Also, we have some cords around the pulleys. What are they? I show them with the purple color. This one, this one, this one, this one, this, and this one. Those are around the pulleys. Those lengths are constant. Okay? I just mentioned that the cord around the pulleys, they are constant. I just write them, but next step, when I want to take the derivative, I eliminate them. Okay? Their lengths are constant. They do not change with time. Means that these terms, if I take the derivative with respect to time, look, the derivative of LT with respect to time equal to derivative of SA with respect to time. And also we have 4SB, I just write derivative of 4SB with respect to time. These are what I have. Also, this one's that with the purple is 0, just the BC, the derivatives will be 0. Or the DE, 0. Or for the FG, 0. For the HI, also 0. For the JK, 0. For the NO is 0. For the PQ, also 0. For the SR also will be 0. Their derivative will be 0. I eliminate them. The remaining are these lengths, CD, EF, this length and this length. Okay? Now, what do you think about those lengths? Are they constant? The lengths of them. For example, CD. The length of CD will be changed or not? No, because it's a two two pulleys that they are constant. The length of the cord between these two pulleys will not be changed. And the lengths between them look like this. This is one pulley, this cord, this pulley, if this one move or this one move, this lengths between these two pulleys are always constant. Also, these are, because they are constant, their derivative will be 0. This one is the constant length, this one also is a constant, this one also is a constant, and also this one is a constant. Means that this is a constant length, this one is constant, this one is constant, this one is constant. And the derivative of constant lengths with respect to time also will be 0. Now what I have here, derivative of LT with respect to time will be 0 because the total length of the cord is constant. This one is the VA plus this one is the derivative of 4SB will be 4 velocity of the B equal to 0. Now we have the velocity of the A, 0. Velocity of the A is positive because this one is the correct direction, is positive. And 0.5 plus is given in the problem. This is the velocity of the A. Plus 4 times of the velocity of the B, the velocity of the block B will be minus 0.5 divided by 4 meter per second. And you will see that this sign, why when this one pull, this block goes up. This direction is a positive. The reason that this one is negative because in opposite direction of the motion. Got it? Questions? I gave you lots of energy during this lecture. Any questions? No? One more. Homework 4. I will upload it tonight. Okay, guys? And I will reach to the home, then I will upload the homework. And the deadline will be on next Thursday night. You will review those questions. If you have any question, you can ask me during the next class time. Okay, guys? I will upload the notes in the Blackboard. You can use. Also, I recorded the class. Let me know if you have any question. Thank you for coming to class. Have a wonderful day. Take care of yourself. See you on next Thursday.
You need to go back to the last slide.
Yep.
I need this. I was like, I was thinking what? I don't want to take myself in. Well,
I'm not gonna fully take my arms.
yeah, another class after this?
You too. Thank you.
That doesn't sound attractive.